Welcome to lecture number 4. This week we're going to talk about vectors, the dot product between two vectors, and the cross product between two vectors. For some quantities, for example mass, time, distance, etc., we only need a number to describe that quantity. But for some quantities, for example velocity, force, etc., we need both a number and a direction. For those, we use vectors. A vector is an object which has a size, its length, and it has a direction. For example, let's suppose we have a vector which has initial point A and terminal point B. Then we call this vector AB with an arrow above it. The length of the vector AB can be written as two vertical lines AB, two vertical lines. The rule is that two vectors are equal if and only if they have the same length and the same direction. It doesn't matter if they have different initial points, it doesn't matter if they have different terminal points. All that matters is that they have the same length and they have the same direction. For example, we can say that AB is the same as CD, is the same as EF, is the same as OP. But note that AB is not the same as GH because the lengths are different. And note that AB is not the same as IJ because the directions are different. When we use a computer, it's standard that we use bold letters for vectors. For example, bold fronted U, bold V, bold W are vectors. That's a little bit difficult when we're using a pen or a pencil. So when we use a pen, instead we use underlined letters for vectors. Underlined U, underlined V, underlined W, etc. are vectors. So for example, if we use a computer, we type AU plus BV, or if we use a pen and we write A underlined U plus B underlined V, then A and B are numbers, U and V are vectors. In two-dimensional space, in R2, if a vector V has initial point 0, 0 and terminal point V1, V2, then we can say that the component form of V is open bracket V1, comma V2, close bracket. And we have a similar idea in three-dimensional space. If V has initial point 0, 0, 0 and terminal point V1, V2, V3, then the component form of V is V1, V2, V3. Think about this vector V. This vector has initial point x1, x2, x1, y1, z1, and it has terminal point x2, y2, z2. We can call this vector V, or we can call this vector PQ with an arrow above it. And I want to let V1 be x2 minus x1. I want to let V2 be y2 minus y1, and I want to let V3 be z2 minus z1. In two-dimensional space, the norm, or the length of the vector V, is two vertical lines, V, two vertical lines, is equal to the square root of V1 squared plus V2 squared. And in three-dimensional space, we have the same idea, except we now have three components. So square root of V1 squared plus V2 squared plus V3 squared. In terms of the vector on the previous page, that's square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. The vector 0, 0 and in two-dimensional space and the vector 0, 0, 0 in three-dimensional space, which we just call bold 0, have norm equal to 0. These are called the 0 vectors. If a vector v is not the 0 vector in either 2-dimensional space or 3-dimensional space, then the norm of v, or the length of v, must be strictly positive. For example, find the component form and the norm of the vector with initial point -3, 4, 1 and terminal point -5, 2, 2. First of all, to find the component form, we do terminal point minus initial point. So q minus -5, 2, 2 minus -3, 4, 1. And that gives us -2, -2, 1. And then for the norm, we do square root of v1 squared plus v2 squared plus v3 squared. So that's square root of -2 squared plus -2 squared plus 1 squared, square root of 9, which is 3. We can think of adding two vectors together in two different ways. First idea is we can imagine we put the vectors nose to tail. What I mean is we draw the vectors u and v so that the terminal point of u is the same as the initial point of v. And then once we've done that, we can draw the green vector, which has the same initial point as u and the same terminal point as v. And this is the vector u plus v. Or we can think of addition another way. Imagine that we draw u and v so that they have the same initial point. After we've completed the parallelogram and then drawn the diagonal is the vector u plus v. We can multiply a vector by a number. For example, if this is the vector u in red, then the orange vector is the vector 2u. These two vectors point in the same way. They point in the same direction, but 2u has twice the length of u. We can also draw 0.5u, 1.5u, etc. They're all pointing in the same direction, but they have different lengths. The vector -2u, it has the same length as the vector 2u, but it points in the opposite direction. Let's talk about subtraction between two vectors. First idea, draw u and v so that they have the same initial point and then complete the triangle, u minus v. Using our idea from before about drawing vectors nose to tail, we can see from this picture that we have v plus u minus v is equal to u. Or we can think of them like this. If we know what v is, then we know what minus v is. It has the same length, but it points in the opposite direction. If we draw u and minus v, then we can add them together, u plus minus v. Let's suppose u and v are vectors and let k be a number. The way that we add two vectors together is we just add their components. So u1 plus v1, comma, and then we add the second components, u2 plus v2, comma, and then we add the third components, u3 plus v3. And we use a similar idea for multiplying a vector u by a number. We multiply each of the components by the number. We get k multiplied by u1, comma, k multiplied by u2, comma, k multiplied by u3. Now, what is the norm of ku? Well, we have our formula. That's the square root of ku1 squared plus ku2 squared plus ku3 squared. We can factor out the k squared, and then we can break this square root into two square roots. square root of k squared multiplied by the square root of u1 squared plus u2 squared plus u3 squared. But the square root of k squared is the absolute value of k. If k is a positive number, then we just get k. If k is a negative number, for example, if k is minus 3, when we square minus 3, we get plus 9. And then the square root of 9 is 3. So we're ending up with the absolute value of 3. And what is the square root of u1 squared plus u2 squared plus u3 squared? That's just the norm of u. So the formula is that the norm of ku is equal to the absolute value of k multiplied by the norm of u. Let's talk about minus u, or which is the same as minus 1 multiplied by u. This has the same length as u, but it points in the opposite direction. For example, let u be the vector minus 1, 3, 1, and let v be the vector 4, 7, 0. Find 2u plus 3v, u minus v, and the norm of a half u. First of all, take u and multiply it by 2, we get minus 262. Take v and multiply it by 3, we get 12, 21, 0. And then add each of these components together. Minus 2 plus 12 is 10, 6 plus 21 is 27, and 2 plus 0 is 2. Next, u minus v, we need to subtract each component from each other. Minus 1 minus 4 is minus 5. 3 minus 7 is minus 4, and 1 minus 0 is 1. And then we want to find the norm of a half u. And remember, norm of a half u is the same as a half norm of u. So I'm going to calculate the norm of u, and then I'm going to multiply it by a half. The norm of u is a square root of minus 1 squared plus 3 squared plus 1 squared. In other words, square root of 11. Multiply that by a half, and we get the answer that we want. Let's talk about some properties of vector operations. Let u, v, and w be vectors. Let a and b be numbers. Property 1. If we have two vectors and we're adding them together, it doesn't matter which order we do them in. U plus v is the same as v plus u. If we have three vectors, it doesn't matter where we put the brackets. U plus v plus w is the same as u plus v plus w. U plus the 0 vector is always just u. U plus minus u is always the 0 vector. The number 0 multiplied by u is equal to the 0 vector. Now, just let me pause here. I'm using the symbol 0 for two different things here. On the left, I have a number. This is the number 0. And on the right, this bold 0 is the 0 vector. Let's continue. Property number 6, 1u is always the same as u. Property 7, a multiplied by bu is the same as abu. Property 8, a multiplied by u plus v is the same as au plus av. And then finally, a plus b multiplied by u is the same as au plus bu. Great, but can we multiply two vectors together? The answer is no, we cannot multiply vectors. Please don't write uv anywhere in your work, because that doesn't mean anything. It's not possible to multiply two vectors together. A vector u is called a unit vector if and only if its length or its norm is equal to 1. So for example, this vector I'm saying is a unit vector. 2 to the power minus a half, comma, minus a half is a unit vector. Why? Because if we calculate its norm, and I'll leave this calculation for you to check, if we calculate its norm, we get equal to 1. That tells us that it is a unit vector. In two-dimensional space, the standard unit vectors are I and j. I is the vector 1, 0, and j is the vector 0, 1. In three-dimensional space, the standard unit vectors are called I, j, and k. I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. Now, note that any vector in R3 can be written like this. We can write it as v1i plus v2j plus v3k. This is two different types of notation for the same vector. Sometimes we will be using the first notation, sometimes we will be using the second notation. If we have any non-zero vector, any vector v where its norm is not equal to 0, then we can create a unit vector just by doing v divided by the norm of v. Why is this a unit vector? Because if we take the norm of this vector, that's the norm of v over norm of v, or norm of 1 over norm of v multiplied by v. 1 over norm of v is just a number. Anytime we have a number inside the norm, we can take it outside as long as we put absolute values in it. But this is not just a number, this is a positive number. So we don't have to worry about the absolute value sign. We just get 1 divided by norm of v multiplied by norm of v. And of course the norms of v cancel and we just end up with 1. So we have two vectors which point in the same direction. V and v over norm of v point in the same direction, but v over norm of v is a unit vector. Anytime we need to find a unit vector which points in the same direction as v, this is the idea that we are going to use. For example, find a unit vector u which points in the same direction as the vector p1, p2, where p1 is the point 1, 0, 1 and p2 is the point 3, 2, 0. First, we need this vector in component form. So what we do is terminal point minus initial point, p2 minus p1. We end up with 2, 2 minus 1, or in this second type of notation, that's the same as 2i plus 2j minus k. We need the norm of this vector. So we calculate square root of 2 squared plus 2 squared plus minus 1 squared, and we get 3. And then the unit vector that we want is p1, p2 divided by norm of p1, p2. The answer to this question is 2/3 I plus 2/3 j minus 1/3 k. An example from a textbook. If v is the vector 3i minus 4j, and let's suppose this is velocity, express v as a product of its speed multiplied by its direction of motion. What it wants is a number, the absolute value of v, or the speed, and then multiplied by a unit vector. So first of all, we need the norm of v, that's the speed. This book, which I took this from, is using single vertical lines for norm, but I prefer to use double vertical lines. The norm of v is the square root of 3 squared plus minus 4 squared, and that's 5. And then we want to calculate the unit vector which points in the same direction of v. So v divided by the norm of v, 3i minus 4j divided by 5. Then the answer to this question is the speed of 5 multiplied by this unit vector. Let's do another one. A force of 6 newtons is applied in the direction of the vector v, express the force F as a product of its magnitude and its direction. Well, the question tells us its magnitude. The question says 6 newtons. So the first part is 6. We also need the direction of the force. In other words, we need the unit vector v divided by norm of v. The answer is going to be 6 multiplied by this unit vector. So we did the same calculation. I won't check the details, and we end up with this answer. Vectors are often useful in geometry. For example, let's say we want to calculate the coordinates of the midpoint of a line segment. All we need to do is to take the average of the endpoints. If I have a point P1 and another point P2, and then I have a line joining them together, the midpoint, let's call that M, is just the average of the coordinates of P1 and the coordinates of P2. So, for example, looking at example 7 at the bottom, the midpoint of the segment joining 3, minus 2, 0, and 7, 4, 4, we do the average of 3 and 7 to get 5, we do the average of minus 2 and 4 to get 1, and we do the average of 0 and 4 to get 2. Our next topic is the idea of the dot product. In two-dimensional space, the dot product of a vector u and a vector v, u dot v is u1 v1 plus u2 v2. In three-dimensional space, we have a similar formula. The dot product of u and v is u dot v is equal to u1 v1 plus u2 v2 plus u3 v3. And we can use the dot product to find the angle between two vectors. The angle is theta is equal to inverse cosine of u dot v divided by norm of u, norm of v. Rearrange this equation. This means that u dot v is the same as norm of u, norm of v cos theta. Let's do some examples. The dot product of 1 minus 2 minus 1 and minus 6, 2 minus 3. First, we take the first numbers, that's 1 and minus 6, and we multiply them together. And then we take the second numbers, that's minus 2 and 2, and then we multiply them together. And then finally, we take the third numbers, minus 1 and minus 3, and we multiply them together. That gives us 3 numbers. Add these 3 numbers together, and we get the answer. Minus 6 minus 4 plus 3 is equal to minus 7. Another example, a half plus 3j plus k dot 4i minus j plus 2k. First numbers are half and 4, multiply them together, we get 2. The second numbers are 3 and minus 1, multiply them together, we get minus 3. And the third numbers are 1 and 2, multiply them together, we get 2. 2 minus 3 plus 2, the answer is equal to 1. Find the angle between the vector u and the vector v. And I've put the formula at the top. We need to calculate u dot v. We need norm of u and norm of v. And then we're going to do inverse cosine of this number. So first of all, u dot v, we can calculate as minus 4. I'll leave this for you to check. The norm of u, please check, is equal to 3, and norm of v, again, please check, is equal to 7. We're going to put these numbers into the formula at the top. So it's going to be inverse cosine of minus 4 over 21. Now, if you're in an exam, you will not have a calculator. So if you're in an exam, this is your answer. You just stop just here. If you're doing the homework and you do have access to a calculator, then you can type these numbers into your calculator and you can find this is approximately 1.76 radians or approximately 98.5 degrees. Let's do another type of question. Again, the formula is at the top in the yellow box. We're going to use this to find the angle theta in this picture, where A is the 0.00, B is the 0.35, and C is the 0.52. The first thing to note is theta is the angle between the vector CA and the vector CB. Let me go back to the picture. Here's the vector CA, here's the vector CV. We're looking for the angle between these two vectors. So we need CA, we need CB, we need CA dot CB, we need norm of CA, and we need the norm of CB. Here's the calculations. I'm not going to dwell on these. You can check these later. After we've got these numbers, we're going to put these into the formula. Theta is inverse cosine of CA dot CB divided by norm of CA norm of CB. So that's inverse cosine of 4 divided by square root of 29 square root of 13. And if we have access to a calculator, if we're not at an exam, we carry on and we calculate that's approximately 78 degrees or approximately 1.36 radians. Two vectors u and v are called orthogonal if and only if their dot product is 0. Now, let me remind you that earlier we saw the formula u dot v is norm of v cos theta. How can this be equal to 0? It could be equal to 0 if u is the 0 vector, because then norm of u is 0. It could be equal to 0 if v is the 0 vector, or it could be equal to 0 if cos theta is equal to 0. When is cos theta equal to 0? When theta is equal to 90 degrees. So the statement u and v are orthogonal. This statement means either u is the 0 vector or v is the 0 vector, or the angle between the two vectors is 90 degrees. If we know that u is not 0 and we know that v is not 0, then orthogonal means that their angle between them is 90 degrees. For example, let u be 3 minus 2 and let v be the vector 4, 6. These two vectors are orthogonal because if we calculate their dot product, then we get equal to 0. And these two vectors, 3i minus 2j plus k and 2j plus 4k, are orthogonal because their dot product is equal to 0. Neither one of these vectors is 0, so we know that the angle between u and v must be 90 degrees. Third example, the 0 vector is orthogonal to every vector u, because if we do the dot product between the 0 vector and u, we always get 0. That brings me on to talking about properties of the dot product. Let's suppose u, v, and w are vectors, and let's suppose k is a number. Property number 1, u dot v is always the same as v dot u. If we multiply by a number k, it doesn't matter where we put k. Ku dot v is the same as u dot kv, or k multiplied by u dot v. We can put the number k anywhere we want. U dot v plus w, similar to multiplying a number a by a number b plus c, we get u dot v plus u dot w. If we do u dot u, we always get the norm of u squared. And then finally, the property which I said on the previous slide, the 0 vector dot u is always the number 0. And again, let me just point out there's two different types of zeros here. The first 0 is the 0 vector, and the second 0 is the number 0. Let's talk about vector projections. Let's suppose we have two vectors u and v. Let's suppose the vector u has initial point P and terminal point Q. Let's suppose the vector v has initial point P and terminal point S. I want to project u down onto v. I want to find the part of u which points in the same direction as v. We can think of that in two different ways. We can imagine that we push down from the top and we're going to squash u down onto v. Or we can think of this as another way. We can imagine that we have the sun up at the top and we're looking for the shadow of the vector u onto v, or in particular, more precisely, onto the line passing through v. This new vector, this blue vector, is called the projection of u onto v. Now, we've got a triangle here. The length of the green side of the triangle is the norm of u. The angle in this triangle is theta. That's the angle between the vector u and the vector v. And the blue side of this triangle is the norm of the projection of u onto v. Or from this triangle, we can see that's the same as norm of u cos theta. Now, I've drawn u and v in such a way that the angle between them is less than 90 degrees, but that doesn't have to be true. We might have that the angle between u and v is greater than 90 degrees. Then again, we want to squash u down so that u is on the line passing through v, or thinking of it another way, we want to imagine there's a sun up at the top and we're looking for the shadow of the vector u on the line passing through v. In the calculation that follows, I'm going to be assuming that the angle between u and v is less than 90 degrees. We could do it this way, and then we would get a minus sign here, and we would get another minus sign later on in the calculation, and then those two minus signs would cancel out. But for the time being, let's suppose that the angle between them is less than 90 degrees. The vector projection of u onto v is the vector from P to R. Now, this is equal to its length multiplied by a unit vector which points in the same direction as v. The length is the norm of the projection of u onto v. A unit vector which points in the same direction as v is v divided by the norm of v. But from the triangle I've drawn here, we know the length of the projection of u onto v. It's just norm of u cos theta, and then we're multiplying by v over norm of v. Let me simplify that a little bit. That's the same as norm of v cos theta divided by norm of v squared multiplied by v. But norm of v cos theta, we know what this is. That's just u dot v. So we're ending up with our formula. This is an important formula, so let's write this as a theorem. The vector projection of u onto v is u dot v divided by norm of v squared multiplied by v. For example, find the vector projection of 6i plus 3j plus 2k onto the vector I minus 2j minus 2k. We're going to be using the formula which I've written in the yellow box at the top. We need to calculate u dot v, we need to calculate the norm of v squared, and then we need to put them into the formula. And here's the whole calculation. U dot v, multiply the first numbers together to get 6, multiply the second numbers together to get -6, multiply the third numbers together to get -4. 6 minus 4 is -4. The norm of v squared would be 1 squared plus 2 minus 2 squared plus -2 squared, or 1 plus 4 plus 4. The answer to this question is -4 over 9i plus 8 over 9j plus 8 over 9k. Another one, find the vector projection of 5i plus 2j onto I minus 3j. What we need to do is f dot v divided by norm of v squared, and then multiply that number by v. So it's going to be 5 minus 6 divided by 1 plus 9, multiplied by I minus 3j. Next example, verify that the vector u minus the projection of u onto v is orthogonal to the projection of u onto v. So here's the picture. Here's u and v and the projection of u onto v. U minus the projection of u onto v is the third side of this triangle. It's the orange vector here. And why is that true? Because when we add vectors together, we add them nose to tail. We can do blue vector plus orange vector is equal to green vector. Because neither of these vectors is the zero vector, we're asked to prove that the angle between them is 90 degrees. Okay, now, clearly the projection of u onto v is some number multiplied by v. So this is parallel to v. That means it's going to be enough to prove that u minus the projection of u onto v is orthogonal to v. So the calculation goes like this. We're going to do the dot product between u minus the projection of u onto v with v. That's the same as u dot v. That's the first part, so u dot v. And then minus the projection of u onto v dot v. There it is. Or u dot v minus u dot v over norm of v squared, norm of v squared. Norm of v squareds cancel out. And we're left with u dot v minus u dot v, which is the number 0. This proves that u minus the projection of u onto v is orthogonal to v. And so therefore it's also orthogonal to the projection of u onto v. Our third and final chapter for this week's lesson is the idea of the cross product. This is another way to combine two vectors together. Again, we're going to need to use our left hand. Imagine holding up your left hand and hold it in such a way that your second finger points in the same direction as u, your first finger points in the same direction as v, and then your thumb is going to give us a new vector n. N will tell us the direction of u cross v. So, more precisely, let n be a unit vector which satisfies these three rules. N must be orthogonal to u. In other words, the angle between them must be 90 degrees. N must be orthogonal to v. We need the angle between n and v to be 90 degrees. And the direction of n is chosen using the left-hand rule. Then the definition is that the cross product of u and v, or u cross v, is norm of u, norm of v, sine theta n. Now, let me just remark, we've got two different types of products here, but they're very different. U dot V is a number, but U cross V is a vector. Look at the formula at the top. U and V are parallel if and only if they're pointing in the same direction or they're pointing in the opposite direction. So either the angle between them is 0 degrees or the angle between them is 180 degrees. But sine of 0 is 0 and sine of 180 degrees is also 0. If we have sine equal to 0 in the formula, then of course we have U cross V equal to 0. Remember this idea for next week when we start talking about more projections. If we try to find if two vectors are parallel, we calculate the cross product and we see if we get the 0 vector. Let me talk about some properties of the cross product. Here, U, V, and W are vectors, and R and S are numbers. RU cross SV, we can move the numbers away from the vectors. That's the same as RS multiplied by U cross V. U cross V plus W, similar for numbers, same as U cross V plus U cross W. V cross U is minus U cross V. I'll talk about that in a moment. V plus W cross U is the same as V cross U plus W cross U. 0 cross U is always the 0 vector. And one which is harder to visualize, but we just learned the formula. U cross V cross W is the same as U dot W V minus U dot V W. Let's just understand if this formula makes sense. V cross W is a vector and U is a vector. So on the left, we're doing vector cross vector, which is equal to a vector. On the right-hand side, U dot W is a number, and U dot V is a number. So on the right-hand side, we have a number multiplied by a vector, that's a vector, minus a number multiplied by a vector, which is a vector. We also have vector on the right. Okay, let's talk about property 3. When we swap the order of U and V, why do we get a minus sign? Well, think about it like this. On the left picture, we use our left hand. We hold our left hand up so that our second finger is pointing in the same direction as U. Our first finger is pointing in the direction of V. And then our thumb tells us that U cross V is pointing upwards. But if instead we wanted to do V cross U, then the first vector is V. So we hold our hand so that our second finger is pointing in the same direction as V, and our first finger is pointing in the same direction as U. But then now our thumb is pointing downwards, so V cross U must point downwards. We've only changed the direction, the length of our vectors are staying the same. So V cross U is equal to minus U cross V. We can use the cross product to calculate the area of a parallelogram. Let's suppose I wanted to calculate the area of this blue parallelogram where the vector U is a vector along one side of the parallelogram and the vector V is a vector along the next side of the parallelogram. Using trigonometry, the height of this parallelogram is norm of V sine theta. The area of a parallelogram is its base multiplied by its height. Why? Because if we cut it just here, and then we move this triangle over here, then we end up with just a rectangle. We know area of the rectangle is height multiplied by base. The base is the norm of U, and the height is norm of V sine theta. So we just get norm of U, norm of V sine theta. But that's almost exactly what we have in the yellow box at the top. The only difference is that we have a unit vector there as well. When we take the norm of u cross v, because n is a unit vector, norm of a unit vector is 1, we just end up with norm of u, norm of v sine theta. So our formula is the area of a parallelogram is the norm of u cross v. And then from there, we can write down the area of a triangle, because the area of a triangle is just a half of the area of a parallelogram. So just a half norm of u cross v. Before we go any further, we're going to need a formula for u cross v. And we're going to be using the standard unit vectors I, j, and k. Now, the first thing to note is that I cross I, that's norm of I, sine 0 degrees n. But sine 0 is just 0, so I cross I must be just the 0 vector. For the same reason, j cross j is 0 and k cross k is 0. What about I cross j? Well, imagine holding your left hand up to your screen and turn your hand so that your second finger is pointing in the same direction as I, and your first finger is pointing in the same direction as j. Where does your thumb point? The answer is your thumb is pointing upward. So your thumb is pointing in the same direction as k. So I cross j must point in the same direction as k. That means I cross j is norm of I, norm of j, sine 90 degrees, because the angle between I and j is 90 degrees, multiplied by k. I is a unit vector, so norm of I is 1. J is a normal unit vector, so its norm is equal to 1. And what is sine of 90 degrees? Sine of 90 degrees is 1. So we end up with just k. I cross j is equal to k. And then immediately, j cross I must be minus I cross j, or minus k. There's another thought to think about, and I'm going to leave this to you. Imagine holding your hand up to this picture, turn it around in whichever way you need to hold it. Please check that j cross k is I, k cross j is minus I cross k is minus j, and k cross I is equal to j. Now that we've done that, we can calculate u cross v. Now, we're going to multiply this together in each component. We're going to do first one multiplied by first one to get u1 v1 I cross I. There it is. And then we need to do first one cross second one. u1 v2 I cross j. And then we're going to do first one cross third one. u1 v3 I cross j. And so on. Keep going, and we're going to end up with 9 terms. Let me bring up the formulae from earlier. First of all, I cross I is equal to 0. So we can cross out this. J cross j is equal to 0. Cross this one out. And k cross k is also 0. Cross this one out. Then we're left with just 6 terms. From the formulae in the yellow box, I cross j is equal to k. So instead of I cross j, we can write k. I cross k is equal to minus j. Instead of I cross k, we're going to have minus j. And so on. Replace each term using the formula in the yellow box. We get 0 plus u1 v2 k minus v1 So u1v3j minus u2v1k plus 0 plus u2v3i plus u3v1j minus u3v2i is equal to, so plus 0. And we can simplify that like this. u2v3 minus u3v2i minus u1v3 minus u3v1j plus u1v2 minus u2v1k. This is an important formula, so let's write this as a theorem. If u and v are these vectors, then their cross product is given by this formula. And this is a formula I'm going to give you in the exams. You don't need to remember this. Some of the people studying this course might have studied matrices and determinants at high school. So if that's true, then you might prefer to use this formula instead. U cross V is the determinant of the 3 by 3 matrix IJK, U1, U2, U3, V1, V2, V3. If you don't understand matrices and determinants, then just forget about this. Use the formula which is now in the yellow box. For example, find U cross V and V cross U if U is the vector 2i plus j plus k and V is the vector minus 4i plus 3j plus k. So using the formula at the top, first I want U2V. U2 is 1 and V3 is 1. 1 multiplied by 1 gives me 1. Then I want to do minus U3 V2. U3 is also 1, but V2 is equal to 3. So it's going to be minus 1 multiplied by 3, or minus 3. And then I want U1 V3. U1 is 2 and V3 is 1. So we just get 2. Minus U3 V1. U3 is 1 and V1 is minus 4. 1 multiplied by minus 4, we have minus 4, and so on. I'll leave the rest of this calculation for you to check. As soon as we know U cross V, then we can write down V cross U straight away, because V cross U is minus U cross V. Next idea, let's suppose we have a plane which contains 3 points called P, Q, and R. Find a vector which is perpendicular to this plane. Well, first, we've got 2 vectors in the plane that we know. We know the vector PQ, and we're going to know the vector PR. And the vector that we want is going to be perpendicular to or orthogonal to each of these vectors. The vector that we want is going to be orthogonal to PQ and it's going to be orthogonal to PR. Anytime we want that, we can just use the cross product because PQ cross PR is always perpendicular or orthogonal to PQ and it's always orthogonal to PR. So to answer this question, we're just going to calculate PQ cross PR. So first we write down PQ and PR. PQ is Q minus P and PR is R minus P. And then we calculate their cross product using the formula at the top. And again, I'm going to leave this for you to check. Please check that PQ cross PR is 6i plus 6k. Next example, find the area of triangle PQR. And this is the same PQ and R as in the previous question. So we already know PQ cross PR. Think back to our formula when we talked about area of the triangle. The area of a triangle is a half of the norm of PQ cross PR. We know that PQ cross PR is 6i plus 6k, so we're going to take the norm of this vector and then we're going to take a half of it. The answer is 3 square root of 2. Find a unit vector perpendicular to the plane containing P, Q, and R. And again, this is still the same points P, Q, and R. We know that the vector PQ cross PR is perpendicular to this plane, but we want a unit vector. So we just need to normalize this vector. In other words, we're going to take PQ cross PR and then we're going to divide by its norm. Again, I leave this calculation for you to check the details of at a later date. A triangle is inscribed inside a cube of side 2 as shown below. Use the cross product to find the area of the triangle. So we know if we have two vectors, then the formula is the area of the triangle is a half norm of vector cross vector. We need to find vectors which point along two of the sides of the triangle. We need to get some coordinates. First thing to do is to draw some coordinate axes. And we can draw this anywhere we want, but for me, it makes sense when I'm drawing this picture to put the origin of the coordinate system on the back corner of the cube. And then after I've done that, I can see that the three corners of the cube are 2, 0, 0, 2, 2, 0, and 0, 0, 2. As soon as I know these three coordinates, we can find two vectors. And there's lots of choices of which vectors we can choose. I'm choosing to use the vector AB and the vector AC. So AB is going to be the vector 2j. AC is going to be the vector minus 2i plus 2k. We need to calculate AB cross AC. I leave it for you to check that we get 4i plus 4k. And then we need to put this into our formula. The area of the triangle is a half norm of AB cross AC. And again, please check the details. Please check that we get 2 square root of 2. We have something called the triple scalar product of u, v, and w. And we need these vectors to be in this order. That's u cross v dot w. What's that useful for? That's useful for calculating the volume of a parallelepiped, which is a three-dimensional object like this. The volume of this is the area of the base multiplied by the height. We know the area of the base because the base is just a parallelogram. So the area of the base is norm of u cross v. The height, using trigonometry, and from this picture we can see the height must be norm of w cos theta. So the volume is norm of u cross v, norm of w cos theta. And that's just the same as the absolute value of u cross v dot w. One final slide, one final comment. We can do the dot product in both two-dimensional space and three-dimensional space, but we can only do the cross product in three-dimensional space. There's no cross product in R2. Why? Because to do the cross product, we need to use the left-hand rule. And we can't use our left-hand rule. We can't have three fingers pointing in different directions if we're only in two-dimensional space. Next week will be our final lecture about geometry. We'll talk about lines, planes, and projections. Are there any questions?